This video is going to be looking at calculating the Q value while using a heating curve. So up until this point, we've looked at two different formulas when calculating Q. We've looked at how to calculate Q when there is a temperature change, which is what we use delta T for. And we've also looked at calculating Q when there is a phase change. So one thing that you'll notice the difference between these two formulas is that there's a delta T in the temperature change for specific heat capacity formula, and then there's no delta T in the phase change. So the reason why we learned these two, and the reason why we can use this in a heating curve, is because you're going to combine temperature changes with phase changes. When you have your different segments in your heating curve, you can add those Q's together to get your total. Okay, so what that looks like, and we are going to use this example. The question says calculate the energy required to change 45 grams of ice at 15 degrees Celsius to water at 85 degrees Celsius. So the very first thing that you want to do when you see both a temperature change and a phase change, because it says it's changing from ice to water, is that you want to draw a heating curve. It doesn't have to be perfect. You just want to make sure you sketch out your plan. Okay, so this is going to be temperature in Celsius. Okay, so when we're drawing our heating curve, we're starting out in the solid phase, then it goes through a phase change as it melts to liquid, and then that's your liquid phase, goes through another phase change, and then it goes to a gas. Okay, so what I want to put in here is where is your ice starting and where is it ending? So negative 15 degrees Celsius. The reason why that I know it's going to go in somewhere in this region is because, remember, we're looking at this for water. So I know that the phase change here for water, it melts at 0 degrees Celsius. It melts and freezes at 0 degrees Celsius. For evaporation or condensation, I know that that happens at 100 degrees Celsius for water. So if I'm starting with ice in the solid phase, which is over here, at negative 15 degrees Celsius, I know that that's going to be, well, I'll just put it about right here. Okay, and that's negative 15 degrees Celsius. Water is in the liquid phase, so I know it's going to be in this section, and it's ending at 85 degrees Celsius, which I'll put about right there. Okay, now what I want to do is break this section down into parts. So right here, I want to start with this temperature change all the way up to 0. So I'm going to break these up into little segments. Okay, so from negative 15 to 0 degrees, that's going to be my Q1. From solid to liquid, that's going to be my Q2. And then from 0 degrees all the way up to 85 degrees, that's going to be my Q3. Okay, just a reminder, we can solve for different Qs and then just add them all together at the end to get my total. Okay, so the first thing I'm going to do is start with Q1. There's a temperature difference from negative 15 to 0, and so that means I'm going to use my specific heat formula. Okay, so what that looks like here is we are going to use Q1 is equal to MC delta T. Okay, and like I said earlier, we're looking at negative 15 to 0 degrees Celsius. So Q is what we're solving for. M is mass, and that's always going to be 45 grams. C is my specific heat. Now remember, this is the specific heat for ice. Okay, it's not the specific heat for water. So for ice, it's a solid, so I'm going to use this value right here. Okay, this is a constant. It's going to be given to you. So 2.108 joules per gram degree Celsius. And then my delta T, remember delta T is your final temperature minus your initial. So we are starting with 0, because 0 is going to be my final temperature minus a negative 15. So when I do that math, I get 15 degrees Celsius as my delta T. Okay, so let's plug these numbers in. Use a different color here. So Q1 is equal to MC delta T. Q1 equals M, which is 45 grams, times C, which is 2.108, and delta T is 15 degrees Celsius. So let's plug that in. 45 times 2.108 times 15. So Q1 is 1,422.9, and this is going to be in joules. Okay. If I'm looking at sig figs, we can make this 1,400 joules. Okay, so this is just Q1. That's the first part. Okay, going back to my heating curve, we've solved for Q1. Now we want to solve for Q2. Now notice that there is no temperature change here. There's only a phase change. So what that means is I'm going to use Q equals M delta H for that. Okay, so Q2 is equal to M delta H. Now we are using the delta H fusion because we are going from a solid to a liquid. So we're going to use this value right here. Going from a solid to a liquid, that's an endothermic phase change, so I'm going to keep that positive. Okay. So Q is what we're solving for. M, again, is 45 grams. And delta H, we said we're going to use delta H fusion, so that is going to be equal to 334 joules per gram. Okay, so plugging these numbers in, we have Q is equal to M delta H. Q equals 45 grams times 334 joules per gram. So when I plug that into my calculator, I get 45 times 334, so 15,030 joules, and for sig figs, 15,000. Okay, so that's my Q2. Now I want to look at my last Q value, which is Q3. Okay, so Q3 is a temperature change. We're going from 0 degrees to 85 degrees Celsius. So if it's temperature change, I know that I'm going to use Q equals MC delta T. So Q3 equals MC delta T. Q is what I'm solving for. M is 45 grams, which is right there. C, now we are going to use the C value for a liquid because we're in the liquid phase now, so 4.184 joules per gram degree Celsius. And then your delta T is your change in temperature. Remember, T final minus T initial, which is 85 degrees Celsius minus 0. So that's 85 degrees Celsius. Okay, so let's plug these numbers in. Q is equal to MC delta T. So Q is equal to 45 grams times 4.184 joules per gram degree Celsius times 85 degrees Celsius. Okay, so when we plug that in, we have 45 times 4.184 times 85, and that gives me 16,003.8 joules. With sig figs, that will be 16,000. Q total is equal to Q1 plus Q2 plus Q3. My Q1 was 1400 joules. My Q2 was 1500 joules, and 15,000, and my Q3 was 16,000. So my final answer, we have 1400 plus 15,000 plus 16,000 is 32,400 joules. And that is my final answer. So it takes 32,400 joules of energy to change 45 grams of ice from -15 degrees Celsius to 85 degrees Celsius.